Okay, I just wanted to make sure I gave you a very practical problem before we leave this section on the dual method. One thing I wanted to mention before I move on, make sure you look at the word problem before this one and read through that one because it's a little bit simpler to solve. But let's take a look at this problem. Pause the video and read it now so that I don't have to read it to you, and that way I can just summarize the problem for you as I set it up. Okay, so basically what we want to do is we want to find out, we want to minimize the shipping costs, and we want to minimize the shipping costs while at the same time satisfy all the conditions. So we need to know how many computers should be shipped on each path. Now I like to draw a little diagram on these types of problems. So this blue circle is plant A and the green circle is for plant B, and the blue arrows represent the shipping from plant A to outlet 1 and plant A to outlet 2, whereas the green arrows represent from plant B to outlet 1 and plant B to outlet 2. And of course what I'm going to do here, you can read here and see, I'm going to let X1 be the number of computers that are shipped from plant A to outlet 1, and X2 is going to be the number of computers shipped from plant A to outlet 2. And then I'm going to let X3 be the number of computers shipped from plant B to outlet 1, and X4 be the number of computers shipped from plant B to outlet 2. Okay, now right here we're given the costs for each of these routes. So this would be 6x1, this would be 5x2, this would be 4x3, and this would be 8x4. That's the total cost. So the total cost for shipping would be $6 for each one that went from plant A to outlet 1, $5 for each computer went from plant A to outlet 2, $4 for each one that went from plant B to outlet 1, and $8 for each one that went from plant B to outlet 2. Now, you have two constraints in the problem. The maximum plant A can assemble a maximum of 700 computers. So the number of computers that leave plant A, or that plant A distributes, has to be less than or equal to 700. Also, plant B has a maximum of 900 computers, so the computers that leave plant B have to be less than or equal to 900. So since X1 and X2 represent the computers that are distributed from plant A, that sum must be less than or equal to 700, and X3 and X4 represent the computers that are being distributed from plant B, so that sum, X3 plus X4, must be less than or equal to 900. You also have some demands. Outlet 1 requires at least 500 computers a month. Outlet 2 requires at least 1,000 computers a month. Well, if you go up here and look at your outlet here, notice that they're receiving computers through two routes. Outlet 1 is receiving computers through the X1 route and the X3 route, whereas outlet 2 is receiving computers from the X2 and the X4 route. So for outlet 1, since it's got to have at least 500, we know that X1 plus X3 must be at least 500. That just means greater than or equal to 500. And outlet 2 must have at least 1,000, so that means that X2 plus X4 must be at least 1,000, or greater than or equal to 1,000. Now, when you put this all together, you get your linear programming model here. This is your objective function, so you want to minimize that function, and you have two less than constraints and two greater than constraints. Okay, well, this is a minimization problem. We know that we can solve minimization problems if all of the variables are greater than or equal to. But these variables, these two constraints are not greater than. Okay, but that's not a problem, because all I have to do, if you'll remember, if you take a inequality and you multiply everything in an inequality by a negative number, so let's say I multiply everything in this inequality by -1, you remember what it does? It flips the alligator over, right? I think some teacher said that at one time, but anyway, it flips the inequality over. So if I multiply everything in this inequality by -1, it flips the less than to greater than. So I'm going to do that for that inequality. It's going to change all the signs. So that'll be -x1 minus x2, flip the inequality over, and the 700 will become -700. Now, I'm also going to do it for the second constraint. Okay, so I'm going to multiply everything in this constraint by -1, so it'll change that to a greater than, and of course it'll change it to -x3 minus x4, flips the inequality over, and you get -900. So now I've got the model here written in standard form. So I can now that I have it in minimization with all greater than constraints, now I can try to find the dual and solve this using the dual method. So the next step is to figure out how I get the dual from this standard minimization problem. Okay, so what we've got here, remember these aren't staggered, so you're going to have to remember you've got like 4. Let me write this in here. Okay, so let's write our coefficient matrix. So this first constraint, remember, only has x1 and x2. So the coefficients are -1, -1. So notice I wrote -1 here, -1 here. There's no x3 or x4 in that first constraint, and the constant's -700. Now remember, I'm not writing the tableau, I'm just writing the coefficients. And now the second constraint has no x1 or x2, so x1 and x2 would be 0 for the second one, but the coefficients of x3 and x4 are -1. So I have -1 here, -1 here, and the constant's -900. Now the third constraint, I have an x1 and an x3. So I have one x1, one x3. So here's 1 for 1x1. I didn't have an x2, so a 0 there. 1 x3, and I didn't have an x4, so put 0 there. And then 500 was the constant. And then the last one has only x2 and x4. So I have 0x1, 1x2, 0x3, 1x4, and then 1,000 for the constant. And then the objective function up here, the coefficients are 6, 5, 4, and 8. So we put 6, 5, 4, and 8. And then we put the 1 here for 1c. Okay, well then, after we get the coefficient matrix, we have to transpose it. Now, you know how to do this. I'll just kind of do the first couple. This row, -1, -1, 0, 0, -700, becomes the first column, -1, -1, 0, 0, -700. The second row, 0, 0, -1, -1, -900, becomes the second column, 0, 0, -1, -1, -900. Okay, and remember, these are y's. We use y values here. Okay, so anyway, you transpose the matrix. Now, from this transpose, we get our dual. So we get our dual. Let's see if you can see it here. All right, so our dual problem, our objective function from the bottom row is -700 y1 minus 900 y2 plus 500 y3 plus 1000 y4. And then the top row gives me minus y1 plus y3 is less than or equal to 6. Remember, these have to be less than or equal to because we're converting them to the dual, which is a standard maximization problem. And then the second row gives me minus y1 plus y4 is less than or equal to 5. And then the third row gives me minus y2 plus y4 is less than or equal to, minus y2 plus y3 is less than or equal to 4. And then the fourth row gives me minus y2 plus y4 is less than or equal to 8. And so that's where those four inequalities down here come from. So that's your four inequalities. Now, so this is the dual problem. Okay, now remember, to solve this, I have to write the initial system of equations. So I have to add to this one x1, I have to add to this one x2, I add to this one x3, and I add to this one x4. So I have to add those original variables as my slack variables. And then my objective function, when I move these terms across the equal sign, they're going to change sign. So minus 700 becomes plus 700, minus 900 becomes plus 900, and 500 and 1,000 both change to negative. Now, we can put this now in a tableau, and again, you're going to have 4 y variables, you're going to have 4 x variables, you're going to have a p variable, and then you're going to have a column for constants. So I'm going to assume that you can follow putting this in the tableau form by now. Now, so this is the initial simplex tableau. Okay, this is just another way to write the initial system of equations. So that actually I meant to cut that out, but anyway. All right, so let me just try to wrap it up real quick here before I run out of time. Basically here you're going to pivot on this column. This is the most negative indicator. You have to ignore this column, this row and this row, because you can only use numbers that are greater than 0 as your pivot element. So you can't use zeros. So you divide 1 into 5 and you get 5. You divide 1 into 8 and you get 8. So since 5 is smaller than 8, that's your pivot row. So we would pivot there. And really what you would do there is you would do minus row 2 plus row 4 to get rid of the 1, and then 1,000 row 2 plus row 5 to get rid of the 1,000, negative 1,000. That's written over here. Now, after you do those two row operations, you're going to get this. Well, you still have a negative number. You have negative 500 here. Well, again, you can't use the zeros. You can only use positive numbers to pivot on. So we would divide 1 into 6 to get 6, and we divide 1 into 4 to get 4. And we have to pivot on this since that's that gives us a smaller quotient. So we do minus this row plus this row to cancel the 1, and then 500 times this row plus this row to cancel the negative 500. And then here, look, we still get a negative. So now we get a negative here. Okay. So, well, let's see what's above this. This is the only negative indicator. Well, I can't use 0 as a pivot row. I can't use negative 1 because you can't use negative numbers. So the only place that I could pivot would be right here. So what I'm going to have to do is I'm going to have to multiply this by, I'm just going to have to take this row and add it to this row and then add it to this row to get zeros there. There already have a 0 here, and then I have to do 300 times this row and add it to the last row to get rid of the negative 300. So finally, I get no negatives on the bottom row. And if you look below the x1 column, you'll see you get 0 for x1. At the bottom of the x2 column, you get 700. At the bottom of the x3 column, you get 500. At the bottom of the x4 column, you get 300. And the P is 7,900. So therefore, C would also be 7,900. So that is your optimal solution. And if you want to, you can actually go back and check, and you'll see that all 4 of those original conditions are satisfied in the original problem. Final comment, when problems get this extensive, that's when you find somebody that's written a computer program that will solve these types of linear programming problems. Okay, I'll talk a little bit about mixed constraint problems in the next video, and then we'll be out of this chapter.